Hello everyone. Today we'll continue with our next numerical. This numerical is different one. See, if you see in this numerical, a continuous beam ABC I am taking, but at point C, internal hinge is inserted over there. Okay, everyone you know that the property of internal hinge is what? Its individual moment on both the sides will be 0. That is, if I consider the moment for member CA and moment for member CB, its individual moment will remain 0, and same is with the thing that its slope will remain 0 again. So if you see the deflecting curve of this, that will be in this way, right, which will produce a different slopes on both the sides. Suppose this is slope on the right hand side, and suppose this is slope on the left hand side. So I am writing this theta CR and this as theta CL over there. Okay, so this will be your basic property for internal hinge, and considering this property you have to solve this numerical over there. Okay, now we will proceed with our steps of solution. Okay, so first step is what? That we calculate the degree of kinematic indeterminacy dk. So degree of kinematic indeterminacy, adjoint A and B both are fixed one, so your degree of kinematic indeterminacy becomes 0. But adjoint C, if you see, you are having different slopes on the either sides over there. Okay, so this dk value, that is theta CL and theta CR, this will be your basic unknowns, so which will be introduced in this dk value. Also along with this internal hinge will be subjected to any one of the vertical downward or vertically upward displacement over there. So total decay for this becomes equal to 3, and which are those? That will be your basic unknowns, that is your theta CL, that is slope on the left hand side of C. Okay, I am considering it clockwise initially, then slope on the right hand side of C, again considering clockwise, and delta adjoint C, suppose it is acting in downward direction. So these three will be your basic unknown values that you have to calculate. Okay, then second step, that will be you are calculating the fixed end moments over there. Okay, now if you observe that loading is given only in member AC over there. Okay, so your fixed end moment for CB member will become directly 0. So we'll calculate MFAC. Okay, MFAC is what? UDL is given to, so minus WL square divided by 12. W is your 40, length is remaining, so length here for AC is 4 and for CB also it is equal to 4 over there. Okay, so W, that is 40 into 4 square divided by 12, that will get as minus 53.33 kilonewton meter over there. Okay, then next MFCA, same value, only your magnitude will get changed, that is restoring moment will be clockwise in nature, plus 53.33 kilonewton meter. Okay, rest your remaining moment MFCB and MFBC, that will remain equal to 0. Why? Because there is no loading given in this span over there. Okay, now we'll move to your next step, that is step number 3 over there. Okay, step number 3, that is what? You'll be calculating slope deflection equations. Slope deflection equation. So first equation, that will be for your member AC over there. Okay, then for member AC, that is MFAC, it is going to be minus 53.33 plus 2EI upon L, plus 2EI upon L, that is 2, length of that is your 4, so that becomes 2 by 4, will get 0.5 of EI into bracket. Now slope at your joint A, that is theta A will be 0, here I am writing, that is your known values, theta A and theta B both will be 0 over there. So theta A will become 0, far end you are having theta C, but that is your slope on the left hand side, so I'll write theta CL over here. Okay, minus 3 delta divided by L, L is your 4 over there, but here you are considering delta because vertical displacement is given here. Okay, that will be your basic unknown. So that is why you have to calculate that vertical displacement, or you have to consider that delta in your equation order. So if you simplify this will get us minus 53.33 plus 0.5 EI theta CL minus 3 by 4, that becomes equal to 0.75 of delta. This will be my equation number 1. Okay, now we'll move for next member, that is MCA. Again MCA, friction moment we have calculated, it is equal to plus 53.33 plus 2 EI upon L will become again 0.5 EI into bracket. Now your far end will be A and near end will be C, so this will become 2 times of theta CL minus this will remain as it is 0.75 of delta. This will be my equation number 2. Okay, next we'll go for next member, that is MCB now. Okay, MCB, MFCB you are having equal to 0 plus 2 E upon L, length is again 4, so that becomes equal to 0.5 of EI into bracket. Now near end is your C, okay, and far end will be B, but here what will happen, adjoint C you are considering now slope on the right hand side, so this will come equal to 2 times of theta CR, that is near end moment, minus 0.75 delta. This will be your equation number 3. But here what will happen, initially we consider here minus over there, but if you consider these two members, that is AC and CB over there, okay, if I consider this delta as my vertical displacement, okay, considering member AC, what will happen here, translational rotations will be induced of anti-clockwise nature, and here translational rotations will be induced of clockwise in nature. So this value comes equal to minus 6 EI delta upon L. Sorry, this comes, we consider that clockwise negative, so anti-clockwise this will come positive and this will come negative, minus 6 EI delta upon L square. Okay, if you can see your our lecture number 1 for this sign conventions over there, we consider here opposite sign conventions, that is clockwise we consider negative. So for this CB member you have to consider this as negative, so minus and minus, that will become here plus over there. We have considered one numerical also based on this, that you can see for this. Okay, so this will be my equation number 3. Next, fourth equation I'll see, that will be for MBC. Again MBC is your MFBC is 0, so plus 2 EI upon L, I'll get 0.5 EI theta CR, because this will be your far end now, plus 0.75 times of delta. That will be my equation number 4. So these 4 equations I am getting as my slope deflection equations over there. Okay, now next step we have to consider the conditions of equilibrium. Conditions of equilibrium. Now if you see the geometry of this beam over there, conditions of equilibrium, you cannot say that moment at A and moment at B will be 0, because these are your fixed support, those will be your capable support, so which will take the amount of bending moment somewhat. Okay, so your whatever these conditions of equilibrium are coming, that will come only at this joint C. As I told you, at your property of internal hinge is what, its individual moment on both the sides will remain 0. So your first property, that will be what, or first condition will be what, MCA shall be equal to 0. MCA shall be equal to 0. Here you can write property of your internal hinge, that is individual moment on either sides is equal to 0. Individual moment on either sides is equal to 0 over there. Okay, so first condition I am considering that MCA is equal to 0. MCA equation we have calculated, that will be our equation number 2. So I'll write that here, 53.33 plus 0.5 times of EI 2 theta CL minus 0.75 of delta is equal to 0. So if you simplify this 53.33 going on RHS side, that will become negative, and this 0.5 EI will get divided to that, so this will get as 2 theta CL minus 0.75 times of delta is equal to minus 106.66 divided by EI, that I'll call it as equation number A, or first equilibrium equation. Okay. Next, second condition that will occur at your second individual moment, that is MCB will be equal to 0 now. That is, we have taken first individual moment MCA equal to 0. This will be my second individual moment MCB again equal to 0 over there. Okay. So MCB equation, that is equation number 3 we have considered here. Okay. I'll write that here. 0.5 EI into 2 times of theta CR plus 0.75 times of delta is equal to 0. Okay. So if I simplify this, 0.5 EI to this 0 will become 0. 2 times of theta CR plus 0.75 times of delta is equal to 0. This will be my equation number B. Now if you observe the equation A and B, here you are having 3 unknowns, theta CL, theta CR, and third unknown is your delta. So these 2 equations are not sufficient to analyze this. Okay. So for calculating these 3 values or 3 basic unknowns, you need to have one more step. That step will be your shear equilibrium equation. It is not necessary that shear equilibrium equation will be only taken for the column members. In case of beams also, you have to consider the shear equilibrium equation. So get this cleared over there. Okay. So for the shear equilibrium equation, in case of columns, what we have done, we have taken horizontal thrusts over there. Okay. Here we will consider the vertical reactions over there. Suppose I am considering the vertical reaction at joint A and vertical reaction at joint B as VA and VB over there. Okay. So these 2 reactions I have marked, like as in case of columns we are marking HA and HT over there for your joint A and D. Here for joint A and B I am marking as my vertical reactions V and VB over there, because here your shear equilibrium equation that will be in vertical plane. In case of frames, that your shear equilibrium equation was in the horizontal plane over there. So here shear equilibrium equation I am considering. So for that I will consider now summation of Fy equation is equal to 0. We consider here upward forces as positive. So this equation what I will get, that is, if you see from this, VA plus VB minus this downward acting UDL, that will be what? Intensity of UDL multiplied by its acting length. So 40 into 4, that will become 160. So total equation I will get as VA plus VB minus 160 is equal to 0. Or you can simplify this as VA plus VB is equal to 60 simply. Okay. Sorry, this will be 160. Okay. Now to calculate this equation over there, I need to calculate the values of VA and VB here. Okay. So for that I need to consider the beam equilibriums over there. There we are considering, in case of frames we are considering column equilibrium. Here we will consider equilibrium of member AC and separately our member CB over there. So first member I am considering here. Okay. This will be your member AC. Okay. Here I am marking your vertical reaction, that is your VA over there. Okay. Next, whatever loading is given to you, keep that same as it is. This is your 40. I am not writing unit over here, you consider that. So this will be your 4 meter. And what you have to do, you have to consider final moments over there. Initially I have told you, you have to consider these signs as clockwise in nature. So this will be your MCA and this will be your MAC. Okay. Same way here I will consider your second beam, that is CB again. Okay. CB, you are having here vertical reaction, that will be your VB. This is again your 4. There is no loading in span CB, so I am not giving here any loading. Only what is remaining, your clockwise moments you have to consider initially, that this moment will be your MCB and this will be your MBC. Okay. So from this I have to calculate these 2 reactions. First is VA and second is VB over there. So for first member I am considering AC over there. To calculate VA, what I need to do, I need to take the moment at joint C equal to 0, considering clockwise moments as positive 1. That is our natural sign convention. So what I will get here, that is MAC plus MCA plus 4 times of VA is equal to 0. So if I simplify this, I will get VA is equal to minus MAC plus MCA divided by 4. Okay, so here what you have to do, you have to substitute the values of equations of MAC and CA. Okay, that is your equation number 1 and 2 here. Okay, so if I substitute these two equations over there, see what I'll get. 1 by 4, and in this both the equation I am having 0.5 EI common over there. Okay, I am having 0.5 EI as common over there. Okay, something is change happening. Okay, sorry, we have not considered here UDL sign convention over here. Okay, so what this will become, see, you are taking moment at joint C, so moment of MAC plus MCA plus 4 times of VA, and moment of UDL is remaining, that will be minus over there, minus UDL moment, that will come equal to 40 into 4 into its lever arm will be taken equal to 2 is equal to 0 over there. Okay, so this you correct over there. Okay, so this how much I'll get, minus 40 into 4 into 2, so 40 into 4 that will become 160, 160 into 2 that will become 320 over there, and 320 divided by this 4 VA, that I'll get as plus 80 over there. Okay, you check this correction over there. Okay, okay, now I'll add these two equations MAC and MCA over there. Now if you see in AC and CA equation, if you add these two units, here you are having minus 53.33 and here you are having plus 53.33. so when you are while adding these two values will become 0. Okay, so I'll not consider these two values in this equation order because they are becoming 0 when you add these equations over there. Okay, now just what I'm getting, 0.5 EI common, so 0.5 EI divided by this 4 over there, I'll get as 0.125 of EI common. Okay, so 0.5 divided by 4. Okay, MAC plus CA, so here if you see, here having theta CL and here you are having 2 theta CL over there. Okay, so that becomes here theta CL plus 2 theta CL, that becomes here equal to 3 times of theta CL, right, and minus 0.75 delta and minus 0.75 delta, that I get as minus 1.5 times of delta plus this 80 as it is. Okay, and this minus sign that will remain over here. Okay, so what I'll do, I'll multiply this minus sign inside over there, so VA equation I am getting as 0.125 of EI into bracket minus 3 times of theta CL, minus minus will become plus 1.5 times of delta plus 80. Okay, so this I am getting as equation of VA over there. Right, now next I have to solve for equation of VB over there. So if you, for taking VB, what I'll do, I'll take again summation of moment at C is equal to 0, treating clockwise moments again positive. So what I'll get here, plus MCB plus MBC. Next, moment of VB along this joint C, that will be your negative moment anti-clockwise, so minus 4 times of VB is equal to 0. So simply VB what I'll get, equal to MBC plus MCB divided by 4. Okay, so VB is equal to, now I have to add the equation of BC and CB over here. Okay, so equation of BC is what, see, that means you have to add equation of 3 number and 4th equation, 3rd and 4th equation. So again from 3rd and 4th equation you are having 0.5 EI common, so 0.5 divided by this 4, I get again 0.125 of EI into bracket BC and CB. So here I am having 2 theta CR plus 1 theta CR, so total I'll get as 3 times of theta CR, 0.75 delta and 0.75 delta, I'll get again plus 1.5 times of delta. Okay, so here VB equation I am getting as 0.125 of EI, 3 theta CR plus 1.5 of delta. Okay, now what I have to do, I have to substitute these two equations in my shear equilibrium equation over there. So here I am writing VA equation, VA plus VB minus 160. Okay, See, now if you see V and VB equation, from both these equations I can take 0.125 EI common. Okay, so I am taking that 0.125 of EI common from this. What I'll get? First I'll write theta CR terms, 3 times of theta CR minus 3 times of theta CL and 1.5 delta and 1.5 delta. So I'll get that 3 times of delta over there. Constant term is remaining plus 80 and minus this 160. So that becomes here equal to minus 80 over there is equal to 0. So if you simplify this equation further, I'll get that as 3 times of 3 I can take common from this. Okay, so that will get multiplied to this 0.125 here. This 80 going on RHS will become, this 80 going on RHS will become positive, taking 3 common and multiplying it with 0.125 here. Total equation what I'll get? Theta CR minus theta CL plus delta is equal to plus 80 divided by 0.125 into 3 EI, that I get as 213.33 divided by EI. So this will be my third or shear equilibrium equation over there, that I am writing as equation number C. Okay, now what we will do, we will solve these three equations, equation number A, B and C simultaneously for the values of theta CL, CR and delta over there. So here I am writing the values here, theta CR first, next theta CL, sorry, first value will be theta CL, second will be theta CR and third value will be delta. So if you solve those three equations simultaneously and you check, you'll get the values of theta CL is equal to 186.67 divided by EI. Okay, second value you'll get as theta CR is equal to minus 240 divided by EI, and third value, that is delta, you'll get as 640 divided by EI. Okay, so you check these values and if there is any correction in these values, then you please comment over there in the comment box. Okay, now we'll move for next step over there, that is step number 6. What we'll do, we'll be calculating final support moments here. We'll be calculating final support moments. Support moments are which one? That is your slope deflection equation, MAC, MCA, MCB and last is your MBC. So you see, you'll get the, substituting this theta CL, theta CR and delta values, you'll get MAC as minus 200 kilonewton meter. Okay, next MCA you'll get 0, MCR again you'll get 0 and MBC you'll get as plus 120 kilonewton meter over there. Okay, and see, for your conditions of equilibrium we have considered your MCA as equal to 0 and MCB as equal to 0, and finally we are getting both values again equal to 0 over there, that MCA and MCB both we are getting 0. Now if you plot the bending moment by superposition diagram, we will see this here A, C and B over there. At C you are having here internal hinge. Okay, so at A I am getting minus 200. If you see sign conventions over there, that minus moment we plot it on upward side, so this will be your 200 over there. You will not write sign over here because already you are plotting it on negative side. Then for your CA member you are getting this value is equal to 0. Okay, next again for CB you are getting this value equal to 0, and for BC you are getting it equal to 120 over there. Okay, so just simply what you have to do, you have to join these support moments by straight lines over there. Okay, now in member AC you are having span moment over there, so that will calculate span moment, or you can say that as maximum span moment over there. Maximum span moment WL square divided by 8, since UDL is given to you, so you calculate that WL square, W is given to you 40 into L square is given to you 4 square, that I'll write as 4 into 4 divided by 8 over there. So if you calculate this, you will get this value as 80 kilonewton meter over there. So 80 kilonewton meter, that will be plotted in this. Okay, so below 120 somewhere, here it will be 80, and that will follow parabolic path. So that comes equal to WL square by 8 is equal to 80 kilonewton meter over there. And just what you have to do, there is no span moment in this CB because there is no loading given to you. And what you have to do, you have to just superimpose this part over there. That is, this will be your BMD by superposition. BMD by superposition. Okay, so hope that you all have understood this numerical very easily. That is, this numerical is asked in your examinations, that is numerical on internal hinge over there. Basically, why I have taken this numerical, to understand the concept of the internal hinge. That is what, that your individual moment on both the sides or on the either sides of internal hinge remains always equal to 0 with different slopes. If you observe these values, theta CL and theta CR, see, you are getting these values differently over there. Okay, so these values will be dependent on your loadings also. If your loading gets changed, your slope values will also get changed, but finally your moment at either ends shall remain always equal to 0 at the place of internal hinge over there. Okay, so here we'll conclude with your first unit, that will be your slope deflection equation. I suggest some assignment numericals to you which are based on the sway frames over there. Okay, so you note those assignment questions over there. See, so this will be your assignment questions over there. So your first question you can note down. See, frame I am taking ABCD and loading is given to, this will be your considered as sway frame. You have to calculate shear equilibrium equation in this, and values I have given for the unknowns, theta B, theta C and delta over there. Okay, same consideration, second numerical I am taking. Only in this case is what, your CD member, instead of it is inverted over there, that is your support is on the upper side. So what will get changed here? Here your delta sign conventions will get changed while calculating the moment of slope deflection equation of CD over there, that these values will come positive over there. Delta you have to consider negative for AB and positive for CD over there. So if you try to solve this, you will get theta B, theta C and delta as 1, -1 and 2 upon EI over there. So you try to solve this. If you are having any doubt, you can comment in the comment box over there. Okay, thank you so much.